Welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're joined by Jen Blank, who is a principal investigator at the SETI Institute. Jen has a Bachelor of Science in Geology from Stanford, a Master's in Oceanography from University of Washington, and a PhD from Caltech in Geochemistry. She completed 2 postdocs in Paris and let me check my notes here. Her second postdoc was at Lawrence Livermore.
The Geophysical Lab.
Geophysical Lab. And she is an astrobiologist who is interested in the survival of organic molecules and has done a considerable amount of experimental investigation into the survival of organic molecules under high temperature and high pressure conditions. And she's a star of the Nova Origins series with Neil deGrasse Tyson, if you've ever seen that. Jen also has something on her CV that you don't see on many SETI Institute PIs, and I want to make sure that I got this right. She was a member of the Science Advisory Panel for Warhead Typing and Kill Assessment Strategy, sponsored by the DoD, and something called the Corporate Lethality Program. Now, with that on your CV, I think that's how you get on a mission to Mars with a laser gun. And Jen's going to talk to us about that today, so if you'll give a warm SETI welcome.
Thanks, Adrian, and no, that wasn't how I got involved in the ChemCam science team. Actually, I owe that to Chris McKay, who reintroduced me to Roger Wiens, who I'd known from the time I was a graduate student, and I sort of came on board the ChemCam science team in 2006. So today I'm going to give you an overview of ChemCam and to describe its capabilities and its background, and then also put it in the context of MSL and the goals of MSL on Mars. And I want to acknowledge at the beginning that a lot of the slides I have in this talk are from the instrument PI, Roger Wiens, and also from help or input from graduate students Anne Olila and Nina Lanza, who I work with at the University of New Mexico. All right, here's an outline of my talk. First, a lot of you probably heard the acronym LIBS, and I'm just going to give you a brief description of what it is. Then I'm going to talk about the pluses and minuses of LIBS for use on Mars surface exploration. And then once again, describe ChemCam and show you some pictures of how the different parts of ChemCam fit into MSL. And then that'll give you some more particulars about the instrument itself. And then actually show you some spectra and describe how we will use ChemCam on Mars. And then briefly give you a description of some of the ongoing development that's needed as we get ready for launch next year. So what is LIBS? LIBS stands for Laser Induced Breakdown Spectroscopy. Essentially, it's a very simple technique. It involves sending short laser pulses to a target and to induce sort of a formation of high temperature plasma. It's been described this plasma is often in excess of 30,000 Kelvin, so it's quite hot. And then when that pulse terminates, and these pulses last on the time scales of nanoseconds, you have essentially very excited plasma, and those excited ions and electrons relax, emitting light. The light's then detected by a CCD spectrograph, and then each line, or each element has unique LIBS spectral lines, and those can be used and interpreted to infer composition of your target material. So here's a little movie. Unlike the picture on my title slide, when we fire the LIBS laser, you don't see a green line. We actually just see a spark at the target. So there it is. And sometimes you hear a clicking noise that's essentially indicating the laser is firing rather than the target being zapped. So what are some of the advantages of LIBS? LIBS is new to planetary surface exploration, and it's actually new to a lot of terrestrial applications as well. It's been around for maybe 15 years, and in the past 10 years, over 250 articles have been written just about the general uses of LIBS. So it's really a technology undergoing rapid development daily. It's a simple technique. It gives you, or is capable of giving you very rapid analysis on the order of minutes per analysis. It has standoff capabilities. So in other words, all you need to do is be able to see the target to be able to analyze it. It's also able to penetrate target surfaces very, very shallowly, but if there are any problems with surface contamination or residues or dust, this offers a way to remove those to get at the innate sample. This technique gives you a capability to detect a whole range of elements simultaneously, both high and low Z, and has very good sensitivities for many of these elements down to the ppm level. And finally, the laser technology requires relatively little power these days, and so that this technique lends itself to portability and also to small payloads on planetary rovers.
How far away can it actually be?
Pardon?
How far away?
It depends on your laser power and your target, a bunch of things. I'll get to this in a few minutes. For ChemCam, we're anticipating distances of up to 7 meters from the target. So, and in terrestrial settings, LIBS is being used nowadays to discriminate hazardous things in toys like lead, to look for chemical weapon residues and contaminants, to look for sources and provenances of food items based on trace element analysis, and more recently actually to distinguish between different strains of E. coli in the laboratory. So there's a lot of potential for this technique. Some of the challenges associated with LIB are outlined here. LIB spectra are sensitive to changes in atmosphere and temperature. So in other words, everything needs to be calibrated. Also sensitive to grain size. Because the LIBS laser spot is typically less than 1 millimeter, you have to really watch where you're pointing it or know where you're pointing it. And it makes it a good tool for simple materials like a metal, but it gets more complicated when you're analyzing heterogeneous materials such as rocks with minerals of various grain sizes, variable grain sizes. And there are also something called matrix effects, which have to do with interactions of ions in the plasma, and these are at this point poorly understood. And finally, there's a limited library of LIBS spectra to date, and we need to have a library in order to characterize and calibrate unknowns and interpret their composition. So why LIBS on Mars? I mentioned before that it has good portability potential, and that it detects nearly all the ranges of elements at various very, very high sensitivity to less high sensitivity. This will give, having LIBS on the next Mars rover will give us the first capability of being able to detect light elements in situ. So that's sort of exciting for astrobiology. And it has implications, again, with this light element detection for being able to do in situ assessment of geochemistry, and particularly with respect to aqueous alteration. The Martian atmosphere poses unique challenges for many of the instruments, both from satellite-based instruments and other surface instruments. And these are things we have to address when trying to get ready the ChemCam. And also, another advantage of LIBS, as I mentioned earlier, is that because you have this ablation capability, you can remove dust coatings on grains or on surfaces and potentially get down to a less altered or more pristine sample. So some of the challenges, and just I want to sort of emphasize that the same sample, because of the sensitivity of the technique, the same sample we analyze in air on Earth will look different if you analyze it in a Martian or other atmosphere, whether it's in space, on Venus, or whatever. And at this point, there's a very limited library of LIBS spectra in the Martian environment. So this is one thing that ChemCam's science team is working to get ready for the mission. And because there's low atmospheric pressure on Mars, that means there will be less interference with the laser signal. So there might be greater signal strength. But because we're dealing with a small portable or a payload instrument, we have a much smaller power than you might use in the laboratory, and therefore that'll decrease sensitivity. So these are competing effects. And finally, the high CO2 concentration in the Martian atmosphere may interfere with emission lines, especially when we're trying to detect carbon. So these are all challenges we're trying to address beforehand. So how does the ChemCam instrument fit into the Mars Science Laboratory, or Curiosity? And just to give a little background, most of you probably know that the initial launch slipped 2 years, and so now our launch is scheduled for 2011. And in this next generation of Mars surface rovers, we're dealing with a much bigger instrument. For comparison, you see the MSL here, Curiosity, versus one of the MER rovers. It's a size, it's about a factor of 3 times larger. In fact, it's hard to tell in this picture, but the size of the MSL is actually comparable to a Mini Cooper. So it's pretty big. There's a large science payload, in particular on this MSL, and it has 9 onboard experiments, the experiments being sort of another name for each individual instrument suite. And that compare that with 6 on Spirit and Opportunity. So what are the goals of MSL? Just briefly, the overall goal is to assess the past and present habitability of the Martian environment. And this is not a direct, but rather an indirect, in this goal would be an indirect search for life, but rather searching for water and habitability and other things that might be considered criteria for habitability. But of general interest is whether or not we can identify organic compounds on the Martian surface or in the first few centimeters of the surface. And also whether or not we might be able to identify any sort of biosignatures, whether they be morphological or chemical. And again, just want to reiterate that the detection of the light elements, carbon and hydrogen and others, nitrogen, phosphorus, are of particular interest to this mission. ChemCam's primary goal is not to be an astrobiology tool, and we're actually pushing to see how we can improve detection limits for these light elements. But the other tools on the MSL include the following here: ChemIn, APXS, SAM, and I mentioned ChemCam. But there are other instruments on board that are going to have a focus on organic detection. In particular, the sample acquisition for Mars instrument, SAM, because it has a gas chromatogram, the mass spectrometer, and it was really designed for detailed analysis of organic compounds. I guess one major difference in the two most powerful tools, the ChemIn, XRD, and the SAM, is that they require bringing a sample on board MSL and then doing an analysis. So in other words, there's sample preparation involved prior to analysis, and so this is both time-consuming and energy-consuming. And so one advantage, again, of ChemCam is that as a scout tool, it will be able to analyze on the order of 50 to 75 spot samples per day. So it takes much less time per analysis and has much less energy requirement per analysis. All right, so going back to ChemCam, as I mentioned, ChemCam will fly on MSL, and this is going to be the first example of an extraterrestrial LIBS. ChemCam itself is a collaboration between NASA and the French space agency, Centre National des Études Spatiales, and our PI on this instrument is Roger Wiens, who's a scientist at Los Alamos National Lab, and the co-PI on the French side is Marie Sylvestre. So both the measurement and the post-measurement analysis are really important or critical to maximize our understanding of the data we're going to collect. Here's Roger Wiens, our PI, standing next to a mock-up that was created by students last summer at Cannes in France. So this is a mock-up of the MSL rover, just to give you well, Roger's not the same size as a Mini Cooper, but it gives you an idea of the scale. Roger's actually about 6 feet tall and quite slim. And this getting the MSL to this point has been a labor of passion and interest for the past 10 years or so. Here's just a sort of a plot for your entertainment of time on the x-axis versus the probability of success of ChemCam. And don't put any exact dates, but there are one or two I'll mention. The concept of having an extraterrestrial LIB came about 10 to 15 years ago, in part among a group of folks at Los Alamos. And actually, our co-PI, the French member, lead rather, Maurice, was actually postdocing at Los Alamos at the time. And there ensued various NASA instrumentation proposals and successful funding opportunities. PIDIP, I think MIDIP came about in about 1998. And then in 2004, they actually put in a proposal to include ChemCam on MSL, and it was selected. And then there was the primary design review and the critical design review. And then here we are today in May of 2010, and somewhere during that period we had a bit of a setback where ChemCam itself was actually de-scoped from MSL. And so that was a period of high anxiety among the team, especially Roger Wiens, who spent 3 months advocating and traveling all around the country to be seen at opportune times by the right people to really help argue that ChemCam could be a very valuable component of MSL. And through a lot of letters and support from the community and some other things that I don't know about, ChemCam was added back to MSL. So here we are today, actually, because of the 2-year slip in launch, we've had a little time to, ChemCam is actually delivered to JPL, and we have had a little bit of time to take it back to Los Alamos, where all the integration has been occurring, and put in an improved suite of detectors and do additional tests in a Mars chamber. And next week, actually, it's going back to JPL to get it ready for launch. So ChemCam is described in its name. It's 2 instruments. It's a chemical tool and a camera. So it's, first of all, the LIBS instrument, and it also has this remote microimager, so we can see what we're pointing at. Someone asked about the standoff capabilities. So we say that we expect standoff capabilities of up to 7 meters from the rover, and this LIBS uses a special, or a rather unusual kind of laser at 1067 nanometers. This is a neodymium, potassium, gallium doped tungstenate. So it's very similar in frequency to a neodymium YAG laser, but it has much higher lasing efficiency at the low temperatures and low power requirements that ChemCam will be working with. It's going to allow us to collect over a large spectral range that encompasses UV, Vis, and the near IR, and that way we'll be able to see a large spectral range of our sample materials. And the RMI will give us monochromatic telescopic images, and it gives us about a 20 millirad field of view, a resolution of about 0.5 millimeters at a distance of 5 meters. And this will give us small scale textural information, and the hope is it'll help us discriminate if we have boundary issues, and just also be able to see where we're looking at in the sample. This part of the mast unit of the MSL contains the laser and the camera and the telescope of ChemCam, and this whole section was actually built by the French part of the ChemCam team. The cost for ChemCam is highly leveraged by the French Space Agency. In fact, I think their contribution is between 2/3 and 3/4 of the total cost for the instrument. And so here you see the laser, the camera for the RMI, and the laser is going to come out and go out, oops, here across the Schmidt plate. I have some arrows to show you this. Here's the laser path, boom. And then it hits the target, and then the target, or it hits the target emits light, and that light's directed back to the 3 detectors, which are actually sitting on the main body of MSL itself. So here's what that looks like in practice. Once again, the laser here, and the laser will be coming out this way toward the target. The body unit, which was built at Los Alamos, includes a demultiplexer and spectrometers. As I just mentioned, the demultiplexer will receive light from the Mast unit, and it's optimized to send light to each spectrometer. These spectrometers are identical structurally, but they have different gratings and surface coatings. And this just again shows the different spectral ranges for each spectrometer. They're essentially stacked together on the body of the instrument. And for the UV and Vis, there's higher spatial resolution of 0.2 nanometers, and then it goes down to slightly lower resolution over the larger spectral range of 500 to 850 nanometers. And here's what the body unit looks like in the flight model. So again, you can see 1, 2, 3 spectrometers all stacked up.
What's the size?
Oh, that's a good question. this is about 3.5 inches. So there, from there to there. So, I don't know if that helps. I have a picture with a Swiss Army knife, but I took it out. Okay, in addition to these two parts of ChemCam, another important element of the ChemCam suite has to do with calibration targets. So these are well-characterized materials that are actually sitting on the rover body and that can be analyzed in an ongoing manner, both on Mars and through comparison with a sister suite in terrestrial labs. These samples are powdered samples and have been tested to show homogeneity to within a 50 micron scale, and they include essentially there are 8 targets. Is that right? Nine actually. Sorry, nine samples plus a piece of metal. So there are 4 samples that are basaltic igneous composition, 4 samples that are sedimentological, and there's 1 sample of graphite to aid for carbon line identification, and then there's also a piece of titanium metal just to do sort of a standardization or wavelength calibration if that's needed. And here's what the target sample holder. The metal titanium piece would be in there. Here they're all together. And once again, the Mast unit, just show their relative sizes, the body unit, and then also a third piece that was added on by JPL is this Mast to body optical fiber connection, which has a lot of thermal insulation that's important for the cold, harsh conditions of Mars. Oh, and the targets. So how do they look on the rover? This again is not the actual MSL, it's the French, the mock-up version, but you can see roughly the approximate scale. So ChemCams in the Mast unit and the spectrometers are essentially sitting on the body of the rover behind the Mast unit, and here are the calibration targets. There's another cartoon of them. Once again, here's, let's see, the ChemCam would be back here behind the masthead. And the principal, I guess the most sophisticated instruments on ChemCam include the SAM and ChemIn, which are front-facing in the rover. So there are lots of these flow diagrams in our operational manuals, and I won't go over them. I just wanted to point out again that we have these procedures and process are in place for testing and making measurements. And that the important point, though, is it typically takes about 6 minutes or 2 hours per an analysis. All right, now I'm going to talk about some of the measurements we've been making. Here's a typical LIBS spectrum showing the full spectral range we can cover. I've sectioned it off by spectrometer, 1, 2, so you can see there's a few gaps in wavelength. And this is actually a sample collected of a basalt, a spectrum collected of basalt and air. And what we've done is we've taken 50 shots and then averaged them to come up with this final spectrum. So once we have the spectrum, what we do is to get essentially the characteristics of our sample, we have all the information for the different spectral lines, and we can categorize those and get quantitative evaluation. Here are some examples showing the ChemCam laser ablation, depth profiling of a small spot at several meters away in air. The profiling rate's about 0.3 microns per pulse or greater. So if we pulse somewhere between 10 to 15 times, you can calculate to figure how much we can get removed from the surface. And we can also remove overall dust in a sort of a larger area by rastering the laser. And here's an example left of hematite-coated quartzite. See this hole of about 500 microns. On the right, we have just basalt powder was just dumped on top of some gypsum, and then the laser was rastered across the surface to reveal the gypsum, the white substance beneath. Here's a depth profile showing that same gypsum sample, and it might be a little hard to see, but in black and blue, you have 2 different sort of numbers of the pulses. The first pulses were in blue, the first 17, and you can see that the spectra changes as you go down to the black one, where we took pulses from a higher number after essentially cleaning off the surface. And so this just sort of evidence that we can get to a slightly different, we'll get a different spectrum if we clean off the surface. Another example here is some measurements made on some Martian meteorites, sugartites. And this just shows, up in the left, shows the Terrestrial one of the Mars meteorites. These are sort of a series of transects across that meteorite. 1, 2, 3, 4, 5, oops. And this shows the pit size of about 500 microns at a standoff distance of the laser of about 5.3 meters from the target. And for comparison, we have the concentration of magnesium and silica in the meteorites. And these are two elements that the LIBS is very sensitive for. And compare in blue and red different LIBS measurements with in black. The black circles are actually bulk composition XRD from the literature. And so you can see we'll get an average composition. We're sort of falling about what's considered to be bulk composition, but once again, we have to be careful to know where we're pointing our laser and assess whether or not it might be representative of a larger sample. So scale is of concern. All right, so here's another summary sample showing for silica some challenges associated with matrix effects, and this is these are a summary of 21 samples that are analyzed, and you'd think there'd be a direct correlation right on that line between the intensity and the element concentration, but in fact we see a bit of a scatter. And we aren't quite sure what's causing the scatter, but we think it's a contribution of these things: laser to sample coupling efficiency, maybe chemical reactions within the plasma, or maybe even collisional quenching. So overall it's pretty good, but there is still this scatter that's takes us away, reduces our accuracy. One way to get around this, we found, is through doing data analysis. The last graph I showed you, that's just strictly from taking peak areas from the raw data. Now if we take the same data and do a partial least squares analysis, we get a much tighter correlation with a direct relation between the measured oxide and the predicted values. So this seems to be a very effective way of tightening our scatter. Another way we're interpreting our data post measurement is through multivariate analysis. And this is another way to actually reduce the spread in your data, but also to help define and compare our overall bulk chemistry results with other sample suites. So this just shows two components, principal 1 and principal 2, which are the two dominant variables in principal component analysis. And this was done doing just essentially PCA work. And you can see all these different circles correspond to different types of rock compositions. This is from the work of graduate student Nina Lanza, where she used a ChemCam engineering model and was trying to see if she could distinguish between igneous rocks and carbonate rocks, and found she could very effectively. It seems pretty primitive to compare, where your sample falls in a circle, but that's actually, of considerable value, and that's how LIBS is applied in general today. I just wanted to give you one example of how the microimager performs, so you can see the level to which we'll be able to see detail. Here's an image of a dollar bill taken at 3 meters, and I'm about to switch slides, and you might be able to see where the laser comes in. So we were aiming for the bullseye, the eye of the pyramid. Did you see that? Maybe not, but it happened right there. And to improve that, here's a difference image. You can see where we hit. So it's just to the right of the eye, right here. But that's pretty good for a 3 meter distance. So we're actually very pleased with that. ChemCam the ChemCam team was part of the first sort of group exercise for the MSL team that involved several different science instrument groups. I don't know if you were involved in that, Adrian, but we worked together over the telephone and through video conferencing to try to do a mock operation or mock operation of a typical Mars day, but in our case it lasted for several days. And someone who wasn't part of the group went out to a mystery location and picked up samples and then took pictures of the samples, and then we tried to analyze them in the laboratory. So it's essentially an inexpensive way to first of all gain group experience working together as a team, and also see how the instruments and using the instruments would fit into essentially a model sole operation day. So this is just these circled rocks here, just some of the samples that were collected and brought back to the lab. And in fact, here's the ChemCam turned out to be a real star in this exercise because of the rapid turnaround and because of the ability to process the data so quickly. Here's again a PCA analysis for the slow motion field test for one of the samples, and again we're just able to show we can distinguish between dolomites, basalts, and a range in gypsum compositions. So again, ChemCam showed its value as sort of the scout instrument. We have a lot of ongoing calibration work that's in progress, and these include trying to establish correlations between sample distance, laser power, and signal intensity, and also make correlations between the range of our training set of standards and the accuracy that we get with ChemCam. We're also experimenting with a number of spots we might need to get a whole rock analysis using samples of different grain sizes and comparisons that way, and also trying to push the envelope for our sensitivity to light elements. And this really requires, we're testing different types of multivariate analysis to see what might give us the best yields there, and try to estimate overall detection limits for Mars conditions. And as I mentioned, trying to apply different multivariate analyses and see which ones will give us the best results for our ChemCam data. These are some pictures that were just taken a few weeks ago when the actual the flight instrument was actually back at Los Alamos, and this whole set of sort of calibration experiments were done. Here's the masthead. Actually, sorry, that's right. There's the masthead at Lanel, both in air and also using a Mars atmosphere chamber. And here's a sort of a summary showing the approximate detection limits we see today. Here's the periodic table, and for large, for some elements we see detection ranges on ppm level. For most of them we see detection limits on the order of 100 to 2,000 ppm level, and for the light elements right now we're down at PPT level, and we're hoping to prove that. So in summary, just want to say that the as I've told you several times now, ChemCam will fly on the next rover to Mars, and it's going to be the first application of LIBS in an extraterrestrial setting. We are working in the ongoing development of spectral libraries and analysis tools to aid in the improvement of our ability to characterize and detect compounds on the Martian landscape. And finally, the overall timeline for MSL now is summarized here. So the final landing site selection is supposed to take place next summer, and I don't know if any of you have your favorite. And then the instruments, or rather MSL, will be shipped to the launch pad next summer as well. The expected launch is November of 2011, and should get to Mars about 10 months later. And nominally the end of the mission, or the mission will last through July of 2014. So thank you very much.
Jen, can I start the questions with, so you're taking a Shergotide as a calibration tool on MSL?
It's one of them, yes.
So you're taking a Martian meteorite back to Mars. That's so cool.
I don't know if it's cool or crazy, but.
Looking at the atomic spectra that you showed, I was wondering how are you sure do you have a pretty good idea of what the excitation conditions are in your samples? Because it looks like you weren't getting, for example, it looks like you weren't getting a big cascade of recombination lines that you were seeing, more like ground state to first excited level lines. And I would have thought you might get a big cascade from recombination from ionized species.
Well, each element has multiple lines that correspond to it, so different intensities. Is that what you're saying? So
well,
and we do
what
see
I saw in that spectra looked more like recombination to lower levels, rather than cascade from an ionized species that was recombined.
Is this the one you're talking about?
Yeah, exactly.
That's an interesting question. I mean, I don't think we can distinguish which are the primary lines. I mean, from this, I mean, what the primary lines would be. So, and which the ground state lines would be more intense and sensitive, because there are a number of things that go into whether or not the detector responds to the different lines. Mm-hmm. So we do see the same lines that recur depending on what laser energy we use. So in terms of their spectral position, the intensities do change. We see very few molecular lines, although we have been looking for C2 and CN molecular lines.
CO maybe?
We have not seen CO.
The CO is pretty stable.
Yeah.
So you might expect more stable than CN. So you might expect to see CO maybe.
I mean, that's interesting. We have not seen
Or
CO.
C2.
Yeah, we have seen C2. In fact, C2 is stronger than in some cases in the just carbon lines. So we're again looking for anything that we can use to help detect the light elements.
Because you can certainly identify most of these lines. Right?
Yeah. Mm-hmm.
Yeah, and so you can see, I mean, if you see H and K calcium, for example, rather than a big cascade from some upper level in calcium where it's recombining.
Yeah.
I mean, that's what I was wondering, whether you were going directly to ground state or whether you were cascading or whether you had like a, well, I don't know.
You know, that would be an interesting exercise. I personally have not looked for the expected array based on which excited states, or if whether or not an element is made it back to its ground state or it's resting in some metastable states.
Yeah.
And that might be
Sure.
interesting to see, to do that exercise to see how it would affect the final spectrum. Okay.
So you talked a lot about calibrating the spectral lines, but it seems like given the precision of pointing that you're going to have some issues with calibrating exactly where the thing is looking at 7 meters and a 0.5 millimeter diameter. So how are you calibrating the pointing after this thing has been shaken to death by the launch and the landing? And
That's a good question. I'm not sure actually. I'm not sure actually how we're going to calibrate the pointing for the RMI. I can't answer that. Sorry, but it's a good question though. You hope there'll be some. I mean, there must be some plan. There must be some plan. I guess defer to the engineers.
I was just wondering if you could just say a few words about the gap in the spectral coverage between the three detectors and why that decision was made. And
a lot of people just sort of might just sort of join those lines together, but I wanted to emphasize the fact that there are 3 different detectors that have a range over which they're effective.
So it was driven by the available instruments and not, there's no lines there, so you don't care?
Yeah, essentially this shows the actual effective range of each of the 3 different detectors that are on board. So it was tried to optimize to give you the broadest spectral coverage, and that's, you know, the spectral coverage you see is determined by the gratings of the spectrometer and also what kind of coatings you have. And so in this case, there is a bit of a gap, but not too many. What is it? 30 nanometers or something like that.
Those detectors are specifically designed to cover those
Yeah. Mm-hmm.
where the gaps take place.
The gaps were not desired. That's just the gaps. The gaps are what I guess resulted from focusing on this near IR and VIS and UV. So does that answer your question? I mean, in other words, we don't want the gaps, but this is the honest representation of what we have. And in fact, this is one of the challenges of working with an instrument that's ongoing rapid development daily now for terrestrial applications. There's been a lot of energy, especially in the military, that's been put into making portable LIBS type instruments. And a big part of the LIBS instrument is the detector array. And but in order to be flight tested and ready for a flight mission, we can't change out the detectors as newer models become available. So we actually were lucky that we were able to substitute detectors that were on the ready to go for a 2009 launch with something that's a little bit more modern for this 2011 launch.
Jen, you mentioned that you had to be careful about overlap of atmospheric absorption with the carbon emission line, and that carbon might be challenging. Given your experience as an organic chemist, how confident do you feel that you'll be able to get good elemental abundances of carbon?
Yeah, that's, I mean, I personally, well, I've done the back of the envelope calculation, which would essentially predicts how much carbon would be in a space that would be comparable to the plasma plume, and it's negligible. But one of the criticisms has been that, oh, since the Mars atmosphere is mostly carbon, are you going to see, is the carbon, if you see some, is that going to be contaminant? So I've convinced myself we have not seen differences in carbon in the laboratory, whether rather depending on whether we do it in a Mars atmosphere or in air. But we're still testing.
At that frequency, you're not going to see a lot of CO2 absorption.
Yep, that's true.
And so you presumably you've used carbonates as a target in your testing in the field as well. What sort of results have you been able to get by looking at carbonates?
The ChemCam team so far has never taken ChemCam to the field. So there are other groups we work with who've taken a portable instrument of similar laser power to the field, and they have analyzed carbonates. But we're limited by just bringing materials from the field to the laboratory. Is that your question? I mean, in terms of for the carbon suite, actually, we have. I showed data for carbonates, but we have Anna Lilla's one of the thrust of her PhD thesis work is to try to determine what the detection limits are for organic carbon in rocks in a Martian atmosphere. And so to that end, we've used stream sediments, lake sediments, shales, and because of all those are variables that determine how well the laser couples with your target material, we have a lot of variables there. And so it's interesting because we're seeing higher carbon lines in, say, for example, a shale sample that has 3 weight % organic carbon determined by other methods, when compared to, or much higher carbon lines in that sample compared to a set of Canadian stream standards that have up to 12 weight % organic carbon. So there's a lot of complexities we're still working out or still trying to explore.
And when you were in the field, were you able to compare your rock samples with the other MSL instruments, what they were telling you?
Oh, with the slow motion field test, yes, the samples were given to the different teams for analysis. So one of the exercises include taking a ground up sample and doing XRD or doing GC extraction and derivatization for GCMS.
Looks like from your drawing.
Sorry.
Oh.
I'll get to you next.
Go ahead.
Oh, okay, sorry.
Okay, sorry. So I have another question about the alignment, back on the alignment of the LIBS with the microscopic imager. So it seems like it would help, right, if you can take an image during the LIBS pulse to actually locate the spot on the surface.
Right.
Would the sequence be like, you take an image before, then during, and then after, and use those to align it, maybe?
That's a good point, and yes, they're supposed to be used in tangent. So in other words, you take the image and then you can essentially see the pit from the ChemCam, or sorry, from the LIBS measurement afterwards, and you can take another image.
Can you image actually during it to see the spot, or is it only like afterwards?
I believe it's just because of the data collection transfer. It's pre or post. It's not synchronous.
But the hit
there's,
is pretty
I mean,
obvious.
in theory, they're supposed to be co-aligned. So
Right.
The
Are they actually
RMI
mounted
is essentially the
through
RMI
the
is a
same
tool.
optics?
Sorry.
Are they actually mounted like through the same optics so that
Yeah.
they're okay?
Yeah.
Okay, that's great.
It looks from your drawing as if the optical that you showed earlier, that the optical axis of your telescope and that of the laser are separated by a few inches. So that suggests that to be focused at 7 meters or closer, there has to be some adjustable toe in between those two. How do you do that when you don't know how far away your target is?
Oh, that's a very good question, and I don't know the actual answer, but there is definitely a procedure for determining distance to the target. So.
I noticed in that spectrum that you have up right now, it looks like there's a nitrogen peak on the right.
750 around there.
Yeah, around 750. Is that due to nitrogen in the solid target, or is that from the atmosphere near the target?
In this case, it's most likely from the air.
And is that because your laser is actually ionizing the air, or is it the heat from the target plume that's doing that?
I assume it's the air is being ionized.
From the plasma stream,
Yeah.
or
Mm-hmm.
okay?
But that, I mean, we don't know exactly. I mean, we don't know for certain.
I just wasn't sure if your laser was powerful enough to actually ionize the air directly.
So this is 50. We used a power for this spectrum of 50 millijoules, and the LIBS or ChemCam will be using somewhere between 15 and 17 millijoules. That's extremely low power compared to, you know, order of magnitude lower than laboratory measurements.
Mm-hmm. Okay.
Okay. If we don't have any more questions,
Oh, I have one.
we have a special pin. I know you probably already have one of these, but you can
Yeah.
perhaps re-gift it to a member of the LIBS team if they do something especially nice for you.
Thank you.
So if you'll join me in thanking Jen for her talk.